Hi, my name is Sarah Kushner, and I'm a PhD student at the University of Toronto. This work is with Risa Ulinsky, David Levine, Karan Singh, and Alec Jacobson. Today I'm going to talk about our paper, Levitating Rigid Objects with Hidden Rods and Wires. The goal of this paper is exactly what it sounds like. Given a scene of rigid objects and some supporting surface, in this case a wall, how can we make the objects appear as if they are floating from a given viewpoint distribution? Our algorithm outputs a hidden support structure such that the objects are held up under the force of gravity and the supports are as hidden as possible. This problem can be seen in many places. This statue of a soldier jumping is held up by rods, which are connected to the building behind it. In this movie set, the actor is suspended by wires, holding him up so that he looks like he's floating in front of the camera. In this 3D zoetrope, each sculpture is held up by a rod. This large whale skeleton is suspended in a museum and requires both wires and rods to hold it up. In reality, making this float is hard to do manually. Experts are paid to make sure all the little parts stay in the right place and that it is sturdy enough for it to be safe hanging in a museum. This problem isn't as easy as it might look. In this example, it seems straightforward, but when we up the complexity of the scene by adding a lot of little parts, or by having a more complicated support surface, or by having multiple viewpoints, the problem becomes non-trivial to solve. What we want is to hold our rigid objects in place under a force. So the question becomes, what do we put between the object and the support surface? First, we sample points on the surfaces of meshes in the scene. From there, we create what is called the ground structure, which is a complete bipartite graph between points on the surfaces. From here, we select edges which will become rods in the resulting truss structure. We solve for the cross-sectional area of those rods. Our method differs from traditional ground structure methods because first we prune edges that we know we definitely don't want in the final truss. For example, ones that go through the object. We use ray casting to quickly determine whether or not this rod intersects the object, and we can discard it. Unsurprisingly, this speeds up our final optimization. Then we want to extract the set of supporting rods. Like I said, most of these areas will go to 0, and we will be left with a set of rods which hold the objects in their prescribed positions and orientations. To do this, we minimize the total volume of the truss, which is the sum of each edge's length times its unknown cross-sectional area. So we minimize the volume, but for a solution to be physically valid, the object must be in static equilibrium. So we want the total force to be equal and opposite to the applied force. Because we are minimizing the volume as opposed to the squared volume, we can find that most rod areas go to 0. This is a topographic plot of the sum of areas. The solution where our force balance equation constraint meets the isolines is a corner of the diamond, which is on the A2 axis, and that means that A1 is exactly 0. This implies that we get sparse solution. In contrast, here's the topographic plot of the sum of squared areas. In this case, the solution is likely to land on a value where both A1 and A2 are non-zero. We want force equilibrium, but we also don't want the rods to break. Rods have a maximum yield stress based on its material, which say how much force a rod can take before it breaks. So obviously we want the force on each rod to be less than or equal to its maximum. So in the axial direction of the rod, we want the rod to be resistant to both pushing, which is compression, and pulling, which is tension. Tension and compression forces are standard in traditional ground structure methods. So unlike those ones, our rods are also resistant to forces in the direction normal to the rods. We want them to be resistant to bending. So we add a linearized shearing force to the rods, which counters this. We show that having shear-resistant rods gives us a less visible solution than without it. By more accurately modeling the strengths of the rods, they are stronger and can be bunched up together, and therefore be less visible. Wires can be thought of as tension-only rods. We care only about the forces pulling on them, since wires cannot be bent or pushed in the axial direction. In this example, a bird is suspended by wires. Wires can be tension-only in the other direction too. Here we show an example where a parade float is kept in place under a buoyancy force with wires. With our framework now, we can balance forces and make sure the wires are strong enough not to break. This leads us to get a so-called perfect single wire solution, but from the video we can see this is unstable. So we also need torque equilibrium so that the object stays in its prescribed orientation. This will happen when the internal torque for an object is 0. Now we get a stable solution where the plane does not rotate. So our method works. It holds the bunny up under the force of gravity. But the rods are very visible from the expected viewpoint. So now we discuss our second goal in this paper, which is to hide the supporting rods from the viewpoints. We want our result to look more like this. Right now we are minimizing the volume and we modeled the static equilibrium equations as hard constraints, meaning that our solution must be physically valid. We also want the solution to be completely hidden, but if we model this as a hard constraint too, we might end up in a situation with no solution. We need to ensure we get a solution every time, even if it is a bit visible. So we have to add to the objective to get a physically valid solution which is as hidden as possible. In order to do this, we need to penalize edges that are very visible to the viewpoint distribution. So we want to give each edge a scalar visibility score. Since we can't see the entire surface area of the rod, only the part of it that's facing us, we can say that the visible area of a rod is its length times its thickness. We assume the visibility to be constant in the normal direction of the rod, since the rod thickness is very small compared to the rest of the scene. But length times radius won't always be accurate. Due to foreshortening effects, we actually want to compute the projected visible area of the rod, which is a function of the angle between the vectors from the viewpoint to either endpoint of the rod. Again, this fits our intuition, since if we are looking at a rod head-on like this, we can barely see it. We can integrate over the rod by uniformly sampling points along the rod and shooting rays from the viewpoint. Now we have a way of computing a rod's projected visible area. But we are not accounting for occlusions. Let's say we're computing the visibility of this rod in the scene with the bunny.
There are parts of the rod which are invisible because they are behind the bunny. So while we are shooting rays, we check whether or not it intersects an object in the scene first and count these hits. We sum them up and weight that value by the angle. The projected visible area of the rod now depends on which samples are actually visible.
And finally, to get the full visibility score, we need to also integrate over the viewpoint distribution. Here you can see the edges in the pruned ground structure colored by their visibility. Now we can add this to the objective, but remember that the visibility we computed is in terms of the rod thickness. So we need to square it, so it can be in terms of the rod's cross-sectional areas. Now we have our full formulation, which is a linear program and can be optimized using standard solvers. Now rods are invisible from the expected viewpoint. Although we use random sampling to create the ground structure, changing the random seed does not qualitatively affect the result. Here we validate our method using fabrication. We 3D printed this bunny and its supporting rods, and then I painted them to match our pictures. We can see that the bunny is held up under gravity and the rods are invisible from the viewpoint. We also have assembled examples made of wooden rods. This ghost is made up of two parts. It has a face which is made up of a hard material, and there is a thin cloth draped over it. We could use the hard object to create our initial ground structure with rod attachment points, and then we can use the thin sheet for visibility since rods can safely hide behind it. The ghost is successfully held up with hidden dowels, and we note here that our solution is also stable to small outside forces like wind. Objects can connect to each other, not just to the support surface. We can see this in the example here. We also achieve a successful result on our complicated example from the beginning, where the supports are invisible from both viewpoint distributions. In this wire-only example, I fabricated it with fishing wire. Something to note here is that we do not need to pre-compute the visibility score since wires are so thin. This is a large-scale example of a sculpture hanging outside of a building. The viewpoint distribution simulates a person's view as they walk into the building. The rods look good from the expected view, but the viewpoint distribution is very wide, so the rods are not hidden throughout the entire path. Sometimes an invisible solution isn't possible using only rods. We need to use a combination of rods and wires. The way our system handles this is by duplicating the ground structure and applying different constraints and visibility weights for each. For the rods, we care about resistance to tension, compression, shearing, and we care about the visibility. And the wires can be modeled using tension only, and we can ignore the visibility score for those edges. Another thing to note is that we enforce symmetry by sampling half of the mesh and reflecting it. Here's another example of using both rods and wires. Rods hold the skeleton together and wires hang it from the ceiling. Normally, a specialist would have to come up with the rods, wires, and attachment points manually, but our system does this automatically. In this example, we can also paint the rods to be the same color of the skeleton and blend in even further. We also fabricate a wire and rod combination example here. We have 3D printed sheep which are held up by fishing wire and wooden rods. Here we can see that the sheep look like they're jumping over the fence, and it's cute. Finally, we create a zoetrope. We run our algorithm on each of the 16 frames in this animation. We hold up the character under gravity and under centripetal forces caused by the spinning of the zoetrope. As we can see from the front, the character doing a backflip looks like they're floating thanks to our hidden supports. Although the supports we generate are hidden, there are some visual cues which we don't account for, such as shadows, reflections, and transparent objects. Here in these pictures you can see that the shadow of the rods is visible. A possible extension of our work is to include multiple ray bounces in the visibility computation, which is similar to how ray tracers work. Thickened rods in the solution may intersect each other. This is a common problem for all ground structure methods, and ours is no exception. However, we have not found this to be a problem in practice during fabrication. Our method also assumes that the input is well crafted. The design process for creating these scenes is non-trivial. In the future, we are interested in pursuing an interactive tool which would provide the user with hints to increase occlusion, or even provide automatic layout options given the objects and viewpoints. Right now, we treat wires and rods completely separately in our system. With the advancement of multi-material 3D printers, it is possible to create supports from mixed materials or even metamaterials. It would be interesting to have a continuous interpolation between different types of rod materials. We thank the funding organizations and thank you for listening.